Welcome to Math Methods lecture on linear ordinary differential equations. Linear ODEs are nth-order ODEs that are of the form an nth-order derivative of y plus an minus 1 n minus 1 first-order differential of y and so on and so forth, down to a0 of x, y of x is equal to f of x. If the right-hand side, so f of x, is exactly 0, then these ODEs are called homogeneous ODEs. The coefficients an of x are in principle arbitrary functions of x. But if they are constants, then the ODEs is correspondingly having constant coefficients. For homogeneous linear ODEs, so for those where the right-hand side f of x is vanishing, we can combine solutions to form new solutions. So for instance, if we have two solutions, y1 of x and y2 of x, both be linearly independent solutions to the ODE in the last slide, with f of x is 0, then we can create a new solution, call it yc of x, by adding the two solutions y1 and y2 of x with two arbitrary constant coefficients c1 and c2. This is easy to prove. Writing the differential equation that we had in equation 4.1 with f of x is 0 as L of y is 0, where L is an nth order differential operator that is spelled out in equation 4.4. We can prove the claim by noting that L of the function y of c is equal to L acting on c1 y1 plus L acting on c2 y2. Since c1 and c2 are both constants, we can pull them out of the differential operator, and we end up with c1L of y1 plus c2L on y2. Since both y1 and y2 are solutions to the differential operator L of y is 0, we find that this is further equal to c1 times 0 plus c2 times 0, or 0. Because of this, a linear combination of two solutions to the homogeneous linear ODE is also a solution to the homogeneous linear ODE. We can obtain the general solution to the homogeneous linear ODE by combining n independent solutions for an nth order differential equation. So formally, we can write down the general solution ygen as a linear combination of the solutions y1, y2, and so on to yn with arbitrary constant coefficients c1, c2, all the way to cn. This works as long as y1, y2, and so on up to yn are all linearly independent solutions. We can test if the solutions y1, y2, and all the way up to yn are linearly independent by considering the so-called Wronskian. The Wronskian is defined as a determinant of a matrix, and this matrix is given in equation 4.7. So the first row of the matrix is just the solution functions y1 of x, y2 of x, all the way to yn of x. The next row is the first derivative of these functions, so y1 prime, y2 prime, all the way to yn prime. And then it continues with the second order derivatives, third order derivatives, and so on, until in the last row, we have the n minus first derivative of the first solution, the n minus first derivative of the second solution, all the way to the n minus first derivative of the solution yn. The point is that if this Wronskian determinant of this matrix, which is denoted as W of these solution functions y1 to yn, is non-vanishing, then the solutions are independent. We can prove that this is the case for instance, second order homogeneous ODE. So let's assume we have two solutions, y1 of x and y2 of x, for the differential equation L of y is equal to 0. And let's further assume that these are not linearly independent. If this is the case, so if these two solutions, y1 and y2, are not linearly independent, we can find two constants, non-vanishing, c1 and c2, such that if we add up these solutions y1 and y2, they both add up to 0. The simplest such case would be if y1 is equal to y2, then we can always find non-vanishing constants c1 and c2 such that these two equations are fulfilled. If these equations are fulfilled, we can find these two coefficients c1 and c2 by writing 4.9 as a matrix equation. So we write this coefficient function matrix y1 of x, y2 of x, y1 prime, and y2 prime dotted into the coefficient vector c1 and c2 is equal to 0. And then we can find non-trivial solutions for c1 and c2 if the determinant of this matrix is vanishing. Of course, the determinant of this matrix is nothing else but the Wronskian for a two-solution basis. So we find non-trivial solutions for the coefficients c1 and c2 for the linearly dependent solutions if the Wronskian is exactly 0. By contrast, if the Wronskian is non-vanishing, we cannot find these two solutions for the coefficients c1 and c2. Hence, the functions y1 and y2 must be linearly independent. A very special case that we want to consider in more detail is when the homogeneous linear ODE has constant coefficients. This is important because in this case we can write down an explicit solution for the homogeneous linear ODE. So if we write this homogeneous linear ODE with constant coefficients as an y nth order differential plus an minus 1 n minus first order differential all the way down to a0 no differential of y of x is 0, then we want to try to find solutions of the form y of x is the exponent of lambda times x, where lambda is constant. If we plug this solution into the form of the linear ODE over here, we find that the nth order differential of the exponent just brings down y of x times lambda to the nth power. Here we have lambda to the n minus first power and all the way down to no power of lambda for the last term here. So we get an nth order polynomial in terms of this coefficient or constant lambda. This polynomial p of lambda is also sometimes called the characteristic polynomial, and the differential equation that we want to solve turns into the statement that we want to look at the zero of this polynomial. Since it's an nth order polynomial, this function p of lambda possesses n, not necessarily distinct roots in the complex domain. I denote this n roots as lambda I, where I runs from 1 to n, and all of these lambda i's have the property that p of lambda I is equal to 0. Let me discuss the simplest case first, where all of the roots lambda I are different, which is the non-degenerate case. In this case, the functions that we get are the exponents of these various roots, lambda I times x. And the claim is that we can find all the linearly independent functions of the homogeneous linear ODE with constant coefficients as these particular y of i's. We can check this explicitly again for the case n is 2 by calculating the Wronskian. So for functions of this form, the Wronskian is easy to compute. It's just y1, y2 prime minus y2, y1 prime. So if you plug in these exponent functions in here, we get the exponential of lambda 1 plus lambda 2 times x. And from this y2 prime, we get a lambda 2. From the y1 prime, we get a lambda 1. But we assumed that lambda 1 and lambda 2 were different. So we find that this Wronskian is in general unequal to 0. And that means that indeed these two solutions are linearly independent. It may happen that one of the roots occurs more than once. And in this case, we call the case degenerate. If only one of the root is degenerate, we can assume without loss of generality that it's root that has index 1. So lambda 1 is assumed to be the only degenerate root, and then all the other ones are non-degenerate. Let's further assume that the root occurs a total of k times, where k has to be less or equal than n, the order of the polynomial. For this case, we construct different linearly independent solutions. Those are given as lambda y1 of x is e to the lambda 1x. That was the same as before. But y2x we construct as x times e to the lambda 1x. y3x we construct as x squared e to the lambda 1x, all the way to yk, which we construct as x to the k minus 1 times e to the lambda 1x. These are the linear independent solutions for the first k functions in the homogeneous linear ODE with constant coefficients. And then the remainder of the solutions are given as before as yi of x is e to the lambda I of x for the remaining n minus k non-degenerate roots, lambda 2 to lambda n minus k plus 1. Let's again do a specific example for the case n is 2. Let's assume that in this case, the first root appears twice. So the degeneracy factor k is also equal to 2. So we construct our two linearly independent solutions as y1 of x is e to the lambda 1x, and y2 of x is x times e to the lambda 1x. If we calculate the Wronskian in this case, we find that the Wronskian is equal to e to the 2 lambda 1x, which is not equal to 0. So that means that we have found the two linear independent solutions for this case. So we discussed the case of the homogeneous linear ODE with constant coefficients where all the roots were non-degenerate and where one root was degenerate. But we can also discuss the case where more than one root is degenerate. If this is the case, we have to build up a set of linear independent solutions as follows. For the first degenerate root, we construct a set of independent solutions as e to the lambda 1x, x times e to the lambda 1x, x squared lambda e to the lambda 1x, and so on and so forth, depending on how what the degeneracy factor of the first root lambda 1 is. After this, we move to the second degenerate root, and we sort of do the same construction for all the degenerate solutions, all the solutions of the degenerate root lambda 2. And then we repeat this process for the degenerate roots lambda 3, lambda 4, all the way to lambda k. And after we've done that, we move to the non-degenerate roots lambda k plus 1, lambda k plus 2, and so on and so forth, and construct the linearly independent solution set out of the exponents of the roots times x. Let me now move to the case where the linear ODE with constant coefficients is not homogeneous, so the right-hand side is non-vanishing. I still want to stick with the case where the coefficients are constant, but f of x is supposed to be non-zero in this case. So we have an inhomogeneous ODE. Unlike the case for homogeneous ODEs with constant coefficients, there's no general solution method for nth order inhomogeneous linear ODEs with constant coefficients. However, there are some methods that are able to solve some inhomogeneous linear ODEs with constant coefficients, and I want to talk about one particular such method, which is called the variation of parameters. So let's again consider a linear ODE with constant coefficient, which is written in the form of a differential operator acting on y of x, and then we have a non-vanishing right-hand side f of x. And the differential operator is nth order, and it has constant coefficients an minus 1, all the way down to a0. If the problem was homogeneous, so if f of x was vanishing, we know how to construct the general solution and all the linearly independent solution for this case from the method that was discussed a few slides back. So I want to talk about what happens if we if we assume that we already know these linearly independent solutions, I ranging from 1 all the way to n. Having these solutions at our disposal, we can construct a general solution for the homogeneous case, which is the combined version of these n independent solutions y1 to yn with constant coefficients c1, c2 all the way to cn. Obviously, this is a solution for the homogeneous ODE, but not for the inhomogeneous ODE. However, we can make an ansatz for the inhomogeneous solution, which I call y subscript p for particular. And this ansatz looks formally very similar to the solution to the homogeneous ODE, which is up here. But now the coefficients c1, c2, and cn, which previously were constants in the case of the homogeneous ODE, are now allowed to be functions of x individually. So we have c1 of x, c2 of x, all the way up to cn of x. All of these are now allowed to be functions of x. Because we allow these coefficients to be functions of x, this is called a variation. So this solution ansatz is called variation of parameters. It's maybe helpful to show how this works out in practice by considering a concrete example. The concrete example I want to consider is the following ODE here. Second order derivative of y plus y of x is 1 over sine of x, also known as cosecant of x. If we look at the homogeneous differential equation, so if we ignore the right-hand side here, we know how to solve this using the solution in terms of the exponents of the characteristic roots. So we calculate the characteristic polynomial for the homogeneous ODE, which from this here is just given as lambda squared plus 1. The roots of the characteristic polynomials, therefore, are lambda 1 is plus I and lambda 2 is minus I. And we can construct a solution based on the fact that these two roots are non-degenerate. So this is a non-degenerate homogeneous case. We can write down the general solution following the method before as c1 twiddle e to the ix plus c2 twiddle e to the minus ix, since I and minus I are the two roots of the characteristic polynomial. It's possible to work through this solution in this form, but since we want to deal with real functions, we can rearrange terms such that we can express y of c in terms of sine of x and cosine of x with two different coefficients c1 and c2. The variation of parameters ansatz is then composed of taking the solution for the homogeneous problem and making an ansatz for yp of x that is supposed to solve the inhomogeneous problem by making c1 a function of x and c2 a function of x. Since we're looking at one particular solution, yp of x, assuming two different functions, c1 of x and c2 of x, is more than we need. We only want to have one particular solution. So that means that in addition to making this variation of parameters ansatz, we can also assume certain relations between these two functions, c1 and c2. In particular, we can assume relations between c1 and c2 that are as convenient as possible for us, as long as it helps us to find any solution to the inhomogeneous problem. It turns out that a useful set of relations that we can assume for c1 and c2 is a condition such as this one. So c1 prime, the first derivative of the function c1 times y1, the first linearly independent solution to the homogeneous problem case, plus the first derivative of coefficient function c2 times the second solution to the homogeneous case is equal to 0. For higher order ODEs, we can generalize this to having multiple conditions on the functions c1, c2, c3, and so on up to cn. So for instance, in addition to a sum that takes into account no derivatives on the solution functions y1, y2, and so on and so forth, we can impose one that has something on the first derivatives of the solution functions y1 prime, y2 prime, and then second order derivatives, and so on and so forth. For second order ODEs, this condition here is perfectly suitable for our needs. So now using the choice for this particular relation of the coefficient function C1 and C2, and using it to express it, the sort of second order derivative of the function we want to calculate in the ODE 429, we find that y double prime plus y prime is given as y prime cosine of x minus c2 prime sine of x. And the right hand side, the f of x, is just given as 1 over sine of x. So then we have this as the differential equation that we need to solve, which is now first order in the differential of the coefficient function c1 and c2. And in addition to this, we have the constraints or the relation that we assumed governs the coefficient function c1 prime and c2 prime. So that gives us two equations, this one, 434, and that one for the two coefficient functions c1 prime and c2 prime. So we can disentangle these two equations for the two functions to have two equations where the functions only appear individually. And those are sort of listed in equations 4.36. So we have c1 prime is equal to cotangent of x, and c2 prime is equal to minus 1. And we can find two coefficient functions c1 and c2 by direct integration of these relations. Doing that, we find the particular solution as a logarithm of sine of x minus x cosine of x plus c1 sine of x plus c2 cosine of x, where these c1s and c2s are now the actual constants that we studied out in the homogeneous problem earlier. To summarize, in these lectures we discussed linear ordinary differential equations, and we learned that for homogeneous linear ODEs, a general solution is given by combining linearly independent solutions. We learned that we can test if solutions are linearly independent by calculating the Wronskian. We also found that for homogeneous linear ODEs with constant coefficients, we can construct an explicit solution. In fact, we can construct explicit solutions for all the independent solutions by finding the roots of the characteristic polynomial. And finally, we talked about solving some inhomogeneous linear ODEs with constant coefficients using the method of variation of parameters. Thank you for your attention.